All right, so we are on lab 3, and this is spectrophotometry. So if you some of you have probably used this, some maybe not, but this is all about how light or electromagnetic radiation can be used and quantified in how it interacts with molecules. And so this is in your lab manual. You have your reading page 63 to 81, and then your write-up, you're gonna have a lab report. And when you look in that lab report, it's going to include the data and analysis of results from page 79 through 80 in your lab manual. And then there are no calculations. There's no calculations section for this one, but there are additional problems on page 80 to 81, and do all of them numbers 1 through 7. Okay, so this is kind of how spectrophotometry works. You have this light source, and this light source is going to go through a lens and a prism, so that you're going to go from having white light to having all the different wavelengths of light. And then you can use this wavelength selector to then say, okay, I just want to shine light that has a wavelength of, pick whatever you like, and that's the light that's going to be shown through my sample. And so inside the machine, you have a cuvette. So this is the cuvette. The cuvette fits inside the machine, and light goes through it in this direction. And so some amount of that light is actually going to be absorbed by the molecules in the sample. And then what light is not absorbed passes through, right, comes out the other side and strikes a detector. And then it's connected to a digital display, and it tells you an output of information. We're going to talk about what those different outputs can actually be. So when you look at an actual sample, right, you're going to look at a cuvette. Our cuvettes actually look just like this. There are kind of two different kinds. One of them is big and open, and so you need a lot of volume in order to use these cuvettes. These cuvettes, which you can see down here, is that they're big and open, and then they net down, they narrow down. And so this is actually the place in the cuvette where light is going to be shown through. So light would come through basically right there and come out the backside, right? And so what you'll notice about these cuvettes are that basically this side is clear, and then this side is frosted and sometimes has ridges and stuff. And so you want to be very, very careful when you're holding these cuvettes that you only touch the side that's frosted. It's frosted because we know that light isn't going to travel through that part of the cuvette. Light's only going to travel through this clear side of the cuvette. And so we never touch that with our fingers, because you're going to end up leaving oily fingerprints, and then it's going to interfere with your readings, and you'll get stuff all over the place, and it'll be crazy. So we use these cuvettes, so we use as little volume as we have to, and then we're very, very careful not to touch them. So we call the light that is coming into the sample, so we have light in, or right here, we call this I, excuse me, I sub 0, or this is our incident light. Incident light. And then some amount of that incident light is going to be absorbed by our sample, by the liquid that is inside of that cuvette. And then the rest of it is going to come out, right? And so we call the light that comes out the emergent light, okay? And so we can actually measure transmittance. We can see how much light is actually transmitted through the sample. So how much light actually comes out of the other side depends on how much you put in, right? So you're going to divide your emergent divided by incident. See, incident. So you could write that IO over I, right? So if you have a sample that is blank, let's say it's not colored, right? It is just water. Then your transmittance, everything that went in should come out. So then your transmittance should be 1. And so we basically set it to that. But usually we do not express transmittance as a simple number. We express it as a percent. So you're going to take whatever value you get, multiply it by 100, and you get percent transmittance. And that's good, but it doesn't necessarily tell us what we need to know about our sample of interest, our protein that's inside of this cuvette. What we really want to know is something called absorbance. We want to know exactly how much light is being absorbed by the sample. That's actually an individual characteristic of the substance, a physical property of the substance. And so to find the absorbance, you take the log of the incident light over the emergent light. And that is what we typically report as absorbance, right? And so you can use what's called Beer's law, or the Beer-Lambert law, as a method to say, okay, if I know the absorbance of something, then I can convert that to concentration. And so there is a formula for that, and it's in your book. And that is, the absorbance is equal to the extinction coefficient, which we do a big pretty E, times the path length times the concentration. So ABS is absorbance. And remember, this absorbance is unitless. Why is it unitless? Because it's the log of a ratio, so it has no units on it. E is our extinction, TIMCT, extinction coefficient, right? And so our extinction coefficient is unique to each compound. So this is unique to each compound at a specific wavelength. So each unique compound has a specific extinction coefficient at a particular wavelength. And so the units on that are going to be 1 over molarity times 1 over centimeters to the -1. Well, 1 over centimeters, right? Which is centimeters to the -1. And so why do you have to have that extinction coefficient having those units? Well, what is L? L is our path length. And our path length is given in centimeters. So your path length, if you come up here, is right here. It's the distance that the light actually travels. So from here to here, that is our path length. That's the length that the light went through their substance. And so for us, you're actually only going to be looking at this path length. So our path length is a little bit shorter. Our path length is 1 centimeter. So you need to write that down, because that is the path length for the cuvettes that we use in the lab. And then last but not least, C is concentration. I'm in highlighter. Know why I'm in highlighter? It's concentration, right? And concentration, our units are molarity, okay? So that's how we use this mathematical equation, and we can convert between an absorbance reading that we get off of the spectrophotometer and convert that into concentration. So we have some sample, we don't know what its concentration is, but if we know its extinction coefficient at a particular wavelength, then we can put it in a spectrophotometer, we can get its absorbance, and then use this formula to convert from absorbance to concentration. And why am I on erase? To concentration, okay? All right, so we can use this formula, right? What did we just say? We can use the formula to solve for the, we said, concentration of, you have to know the substance, you have to know what it is. So it's an unknown in the sense that we don't know the concentration, but we know what the substance is. So concentration of a known substance at an unknown concentration. So you have to know what it is, you just don't know how much of it's there. So the controlling factor is, in order to do this, we have to be able to fill out all of this equation. What else do you need to know? You need to know the path length. Well, I gave you that. The other thing you need to know is this extinction coefficient. So you must know the extinction coefficient. Didn't give enough room for that substance at the particular wavelength that we use in the experiment. So you're going to get an extinction coefficient that is specific to your protein at a particular wavelength, right? And so what we're going to do is we're going to use this concept later on in the year, in the semester, and we're going to purify a particular protein. And that particular protein is lactase dehydrogenase. It's an enzyme that will convert lactate to pyruvic acid. And so in this reaction, right, you not only have our lactate going to pyruvate here, but we also have something else going on. We have NAD plus being converted to NADH. So this is an example of a dehydration reaction, right, where we have a secondary alcohol, right, and our secondary alcohols in our lactate, right? So here's our alcohol, and then we look at the carbon that's attached, and you have 2 R groups attached to it, so that's a secondary alcohol. And that's being converted into a ketone, where we have this C double bond O, and then that carbon is then attached to 2 other 2 R groups. So that's a ketone. So the ketones in pyruvate, the lactate is the secondary alcohol. So in this reaction, you actually have an electron and a proton that are converted and transferred to NAD+. So NAD+, you get from here, you get an electron and you get a proton, right? And then you also have an extra proton that gets released. But so we said an electron, I put that as E-, and a proton P+, right, are transferred to NAD+, and we're going to make NADH, right? So we have kind of 4 different substances that we can look at in this reaction. And so whenever you look at a reaction, what you can do is you can plot versus time. So time's going this way, right? You can see what happens. Here's a reactant. What should happen to reactants as time progresses? Those reactants should drop, right? Because why? They're being converted into products. So products should increase over time. So you can monitor the reaction, the progress of the reaction, by looking at the decrease in reactants over time, or you can look at the increase in products over time. Either way, you're monitoring the progress of the reaction. But really, we do have a preference. We really would rather look at the products, because in the very, very early time point, it's hard to see a small drop when you already have a high concentration of something. So what we would prefer to do is to look at the products, because you can see a small increase when you're starting out with basically nothing, and then you're creating more and more of your product. That's easier to see those small changes in the beginning of a reaction. So we prefer to monitor the product. So in our lactate dehydrogenase catalyzed reaction, we really don't have a way to measure pyruvate. We don't have a way to measure NAD. Oh, why? NAD. And we don't have a way to measure pyruvic acid. Right? And so what can we do? Well, we want to measure NADH. We can measure NADH. And I think I deleted something here. Let's see. We don't have a way to measure NAD or pyruvic acid, right? Okay, but what we can do, let's just insert it here. So we can monitor production of NADH, right? We can, because why? Because it has a unique extinction coefficient. So we can measure production of NADH because it has a unique, so because of, and we're going to say unique extinction coefficient, that's that pretty E that you see in the epsilon that you see in that method. And that has to be at a particular wavelength. And so this one is at 340 nanometers. And so we call this the direct method. in protein quantification. If you want to know the amount of protein that you have, this is the direct method. We take the absorbance, we know the extinction coefficient at that wavelength, and we convert it directly to concentration. So what do you need to know? You need to know the extinction coefficient for NADH, because that's what you're going to be quantifying. So at 340 nanometers, that extinction coefficient is 6,220 cm minus 1. Okay. So this relationship between absorbance and this is not supposed to be time. This is actually supposed to be concentration. Concentration, right? So as your concentration goes up, your absorbance goes up. And what we can see is as we increase that concentration, well, our absorbance goes up. So we have a linear relationship. Okay, so that linear relationship works to a certain point. So once you get above about 1, an absorbance of 1, then you stop becoming linear. So your absorbance, the absorbance is, if you go above or below a certain concentration, the relationship between concentration and absorbance is no longer linear. Right? It's linear only for a portion. So for our experiment, in order for it to work, we are going to get 2 absorbance readings that are in that linear range. So what is that linear range? You want to be between 0.8 and 0.1. That's my range that I'm going to give you. Because if you get above 1, and really when you get close to an absorbance value of 1, what's going to happen is your molecules are going to be so dense, you're going to have so many particles that when the light comes in, the particles that are basically in front are going to absorb the light, and they're going to hide these other molecules that are basically hanging out behind it. So basically you have too high of a concentration, and so you're going to end up getting an absorbance reading, and then your concentration is not going to be accurate. So if you look at a concentration versus time, you know, our theoretical is that it's linear, but what's going to happen is you're going to get to a saturation point. So in real life, it's not quite perfect at the beginning, and it's not quite perfect at the end, and it's going to level off like that. And so you want to stay in this linear range. So this linear range is 0.1 to 0.8, okay? So what happens if you make a sample of NADH, you go to the spectrophotometer, and it has an absorbance that's greater than 0.8? What do? Then you're going to have to make some serial dilutions. And I'm giving you a hint right off the bat. I'm telling you that the sample of NADH that I'm going to give you, it has an absorbance value of greater than 0.8. So you are going to have to make some serial dilutions. So let's talk about serial dilutions real quick and how you're going to do that. So I always want to know the initial concentration of this sample, or the initial absorbance of this sample, so that I can convert it to concentration. So I'm going to make some dilutions, right? So if I make my dilutions, how do I go back and calculate the absorbance of my initial sample, right? So my absorbance, so absorbance of my dilution is that absorbance times all dilution factors used. Dilution factors used. And I'm going to give you some examples, okay? So let's look at what I've drawn here. We have an initial NADH of unknown concentration, right? And I'm telling you, I know that it's going to be greater than 0.8. So I'm going to go ahead and make a couple of dilutions and see where I'm at in order to get that one that's between get 2 that are between 0.1 and 0.8. So how do I do tube A? If I'm going to do tube A, well, in order to do tube A, I'm telling you here, this is a 1:4 dilution right here. So to get to tube A, I did 1 ml of my initial, and I added to that 3 ml of DI water. Always going to use DI water, for a total of 4 ml. So that gives me a 1:4 dilution, right? So That's my tube A. So if I take an absorbance reading of tube A and I get an absorbance of 0.4, then I'm going to take that and I'm going to say multiply by 4, and that's going to give me my initial NADH value of 1.2, right? 12, 16, no, 16, 1.6, haha. Simple math, okay? So that's tube A. So if I want to know in tube A how to get my initial absorbance, I'm going to take my tube A absorbance, AB absorbance, and I'm going to multiply by 4, and I'm going to get my initial absorbance, right? My undiluted was too high, and that's why I couldn't use it, and that's why I had to make these dilutions. So let's talk about tube B. Tube B, I'm doing a 1:3 dilution, right? So what's a 1:3 dilution? You have to do 1 ml of, oh, but this is a serial 1:3, right? So it's 1 ml of tube A plus I'm going to do 2 ml of DI water. So I'm going to get a total of 3 mils. So that's my 1:3 dilution. So if I want to know from tube B what my initial unknown concentration was, I'm going to take my tube B absorbance. I'm going to multiply that times every dilution that was used. So I'm going to have to multiply it by 4 because that's the one I did right here. And then I did a second dilution that was a 1:3. So multiply that times 3. That will give me my initial sample's absorbance value. Okay, and then if I did tube C, that's a 1:2 dilution of B. So that's like 1 mil of B and 1 mil of water, and that's C. And so I would take my tube C absorbance, multiply times my first dilution, which was a 1:4, my second dilution, which was a 1:3, and then my third dilution, which was a 1:2. That gives me my initial absorbance. Okay. So be careful and make sure of a few things when you do this. Before you make each sequential serial dilution, vortex your tube that has all your solutions in it. And make sure that you have at least 1.5 mils of each dilution when everything's all said and done, because that's the minimum volume that you need in order to read inside of that cuvette. So you can use any dilution. You do not have to do this 1:4, 1:3, 1:2. This might not work. It probably won't. You can use any dilution you choose, as long as when you put, let's say, tube A and tube B, both of these have an absorbance reading that are between 0.8 and 0.1, or maybe tube B and tube C. These have absorbance readings between 0.8 and 0.1, okay? And then the other word to the wise is to make sure you first blank the spectrophotometer with a cuvette of water at 340 to make sure that that water is not, you're not picking up absorbance from the water. You're only picking up from NADH, okay? So that's the first kind of part. So this was up above here. This is all part A, the direct method of protein quantification using spectrophotometry. So now we're going to talk about part B. So this is called the indirect method. So in the indirect method, the problem is that you have this reactant or product, but you do not have a unique extinction coefficient. I'm just going to abbreviate that. You don't have a unique extinction coefficient. So if you don't have the unique extinction coefficient, you can't do a direct method. So you got to kind of think about what else could we do? Well, we know that aromatic amino acids will absorb light at a particular wavelength, right? That's at 280 nanometers. And that would be okay, but the number of aromatic acids in a protein can vary. So unless you know how many you have, then you don't get an accurate conversion. So that's not really, so that would not be a great measurement technique, right? You can make it work, but So what we typically use instead is a colorizing reagent. or sometimes they call it a tag. Either way, it's the same thing. And so this reagent is going to react with a certain part of the protein. And then once it's in that complex, once it's bound, then it's going to result in a color change. So you're going to have a colored complex of the tag plus protein. Then we can measure that color, the formation of that color, in what's called a Bradford protein assay. And so this is our indirect method, okay? So in the Bradford assay, that tag that once it's bound that's going to change color is called Kamasi Brilliant Blue. Brilliant blue, okay? So when it's alone and it's unbound, it's not in the presence of any protein, it is red. But when the tag is in a complex with a protein, then it's blue. So we can monitor absorbance in the blue spectrum at a blue wavelength, and that is about 595 nanometers, okay? But here's the problem. Sure, we can do that and we'll get a value, but we have no correlation to link concentration to intensity of light or absorbance, right? So what we have to do is we have to construct a standard curve. So you take known concentrations of your protein and mix it with this Kamasi Brilliant Blue, and you create a standard curve, and then you can identify your unknown. So in part B of this lab, you're going to have two protein samples. They're both going to be BSA. Those samples with, it's called bovine serum albumin, and we just abbreviate that BSA. So you'll have two protein samples of BSA. They're both BSA. One of those samples is our known KNOWN, known concentration BSA, okay? The other is our unknown. Okay, so the stock is what we know, known, you could call this the stock, right? And so what we do is we create the standard curve with the known or the stock. Known / stock BSA. And so that stock solution that I'm going to give you in lab is at 1 milligram per milliliter, right? Now, 2 seconds real quick, let's think about units. 1 milligram per milliliter. When you do your calculations for this lab, you're going to have to be able to convert, because a lot of things ask you for, like tables will ask you for micrograms per microliter, right? But here we've got milligrams per milliliter. So what's the difference in those? If you do dimensional analysis, what you should be able to prove to yourself and to be able to switch between is that 1 mg per mil, that 1 mg per mil is exactly the same thing as 1 microgram per microliter, right? It's the same thing. So if you don't believe me, please do the dimensional analysis, all right? So in this, these samples right here are going to be your standard curve. Standard curve, okay? Then these are going to be our unknown BSA, right? So to make the standard curve, you need a couple of different concentrations. Now your book wants you to do way more concentrations than I want you to do. So these are the concentrations I want you to do. I want you to do 0 micrograms per microliter, 10, 20, 50, and 100. Okay, your book has some extras, but these are the ones I want you to do. We don't know the absorbance. This is what you're going to measure with the spectrophotometer. Microliters of unknown BSA. You should not be using unknown BSA in this part of the experiment. What you want to use is you want to use that stock, that standard BSA that you know is 1 mg per mil or 1 microgram per microliter. So if it's 1 microgram per microliter, right? If we want 0 micrograms, we're going to put a 0. If we want 10 micrograms per microliter, all we need is 10 microliters, right? 20, you need 20 microliters. 50, you need 50 microliters. And 100, you need 100 microliters. Okay. Now, you want to make sure that in the end, every single one of your samples has the same total volume. This prevents you from having a dilution effect on your results. So the maximum amount of standard BSA concentration you're putting in is 100 microliters. So you're not going to put any extra water to fill it up to 100 microliters. But all the others you want to bring up to 100 microliters. So our first one, we're going to put all water, right? Next one's 90, then we have 80, then we have 50, right? And then in the end, they all have 100 microliters between these two columns. And at last, you need the Bradford reagent. It's the reagent with the Kamasi Brilliant Blue. And what you're going to do is you're going to put 3 mLs in every single sample, right? Now, here's my tip to the word to the wise. Make sure when you're making that standard curve, as soon as you add Bradford reagent to tube number 1, you immediately vortex it. Don't wait until you get all your standard curves done, all your tubes for the standard curve. Do one at a time. Vortex it, put it on the side. Do number 2. Vortex it, put it on the side. Add it to number 3. Vortex it, put it on the side. Okay, one at a time. So I drew this big black line here because this is telling you this is the data for the standard curve. Everything above here is the standard curve. Now that is going to give you data so that you can graph absorbance at 595 versus our BSA concentration. And so when we do that, we'll be able to plot this data. And once you plot the data, you're going to do absorbance here, right? And then protein concentration. So you're going to perform a linear regression of the data. So it's a line of best fit, right? And so you're going to get 2 things from that. You're going to get your equation of your line, and it'll probably have mx plus some number, 0.00123, something, you know, but it's in that format of y is equal to mx plus b. And so you want to really make sure that you include your equation and your R squared value. Your R squared value tells you how accurate, how close all those data points are to your line of best fit. If you have an R squared value that is 1, that is a perfect fit, which I do not expect you to get, but you should get something pretty gosh darn high. So maybe like 0.97 is kind of the lowest you probably want to see. It's really easy in Excel. If anybody needs help with this, they can you can ask me. But Excel is super easy, and then you can just print it out and tape it into your lab notebook, right? So you remember the equation of lines, y is equal to mx plus b. So if you put the data in like this, y should be your absorbance, and then x should be your concentration, right? So you need to go and do your unknown concentration BSA, right? And you're going to do it in triplicate, right? So 100 microliters for each. So let's come up here. So now we're going to do this. This is going to be our sample, and we're going to do 100 microliters of, oh no, I'm in the wrong spot. In the wrong spot. So this is our, we don't know what is our concentration. That's our unknown. We're not sure. This is the data you're going to collect, and then you're going to do 100 microliters of your unknown. You're not going to do any standard BSA. You don't need any water, and you're going to still add 3 milliliters of Bradford. So 3 ml, right? 3 ml, 3 ml. And then you're going to take your absorbance reading. So once you have your absorbance reading, you're going to say, okay, my absorbance is equal to 0.3 for my unknown. So I'm going to come over here to 0.3, and then I'm going to say, okay, well, what does that tell me about the concentration? And so you can plug that into your y is equal to mx plus b, you plug in your absorbance value for y, and then you solve for x, right? And then you can find your concentration of your unknown. All right, so that is it for hold on. For us, what I want to do real quick with y'all is just to talk about a few things about the lab in particular. Do not put your pipette tips in my stock solutions. You can use a clean transfer pipette to take some out and put it in a tube for yourself, right? Now I'm going to give you a few hints on completing the lab in a timely fashion. Complete it in reverse. So the indirect method, part B, where you have your BSA and you have to add your Bradford reagent, it's going to have to incubate with that Bradford reagent for 10 minutes, right? And so while that's incubating, if you start on BSA, let it incubate for 10 minutes. And while that incubation is happening, go ahead and work on part A. Then once part A is completed, then go back and measure your BSA. So it'll just make your life a little bit easier. And the other thing is to be very, very careful about what wavelength you're using for which sample, right? And then when you have a test tube, like you're gonna have a test tube that's gonna have whatever sample in it, and then you're gonna have your cuvette, and I'm a really terrible, terrible artist. I can't really draw that, but you don't actually have to pipette it. You can actually just pour until you make sure, if I come up to the top, make sure that when you pour, you go above this line right here. So you want to make sure that you're putting enough that you're filling this entire bottom portion of the cuvette, because that's actually the part where the light is going to go through. So you see it where it necks down. You just want to leave a little bit on top of that part where it necks down, and you'll have plenty of sample. So that's about 1.5 milliliters, but you don't have to measure and be precise. This is one of those, just pour, make sure you have enough. Okay, and I think that is it. All right, good luck.